Right, next now we're going to look at, this basically means graphs. I for current, V for voltage. Okay, write that down. Whoops. Got it? Yep. Okay. Right, so I want you to look and draw this circuit. So this here is a battery, ammeter, voltmeter, resistance, and does anyone remember this symbol? Variable resistor. You can change the resistance on this one. So please draw this first, carefully. Did you draw this, KJ? Already? Is it beautiful? Let's see this work of art. Not bad. Not bad. Would I say beautiful though? I don't know. Alright, have you drawn it? Yep. Everybody drew this? Okay. So let's have a look at what's happening here. So I think we have battery here, and then there's an ammeter here, and then there's a resistor here, and then it's not on the picture, but really I should have put a switch in here somewhere as well for safety. So we'll imagine there's a switch here and it's closed. What was down here? Oh, the variable resistor, wasn't it? And then also, up the top, there's a voltmeter around this. So what happens is you close the switch, the current goes on through the ammeter, through the resistor, along it goes, and then through the variable resistor, and then back to the start. Okay, I don't tell you, it's not important to know, but I don't tell you the voltage of the battery, okay? So let's just say it's E here. I don't tell you the voltage here, well sorry, you know the voltage here because you can see the voltage on the voltmeter, so you can see it here. Do you know the voltage here? No. In the variable resistor. Do you know it? No. So I'll just call this voltage here V var for variable. Okay? Do you know what the current is? Yeah, do you know the current? Yeah, you can see the current here. So let's call that current I. Is the current up here the same as down here? What do you think? The current that you see here, okay, is it the same current that's here? Yes, it is. Because if you remember, current is the same in series. So the current here is the same. Now do you remember you have the formula V equals I or, and I'll write or var to mean you can change it. Remember, you can change this one.
V is equal to I over R.
No, V equals I or. I'm certain of this. hang on. Am I certain of this? I am certain of this. Okay. Can anybody tell me what they think V plus V var equals? Anybody got any ideas here?
I is equal to V over R.
Yeah, so what does V equal? Yeah. Now let me.
Because I use the example in the class.
Yeah.
Over.
V equals I R.
Over.
V equals I over R. Where's your triangle you drew? Remember the triangle?
I just wrote it down.
Yeah, but why didn't you draw the triangle?
That's it.
Uh-huh. Yeah, that's the same formula I'm using.
E is total.
Yes, total voltage, yeah. So if you remember, do you remember voltage adds together? So if this is voltage V1 and this is voltage V2 and they're together, the total voltage is V1 plus V2. Okay? So here you have voltage at the top of V and voltage down the bottom, V there. So the total equals E. That's from the battery. Yep. Now this is what I want you to see. What happens if I make this increase? What happens to this? It increases also. So if I make this increase, this one here increases. If this one here increases, then my question is, what happens to this one? Very good, it decreases. Because the total must be E. The battery voltage doesn't change. This is like a fixed battery. So if this gets bigger, then this one must get smaller to keep the total the same. Yeah? So, as we increase this one, what happens to this one? It decreases. Now, the point I'm trying to make here is, what you can do is, by changing the resistance on the bottom, you can change the voltage on the top. That's what I'm trying to say is happening here. Okay, so as you change the voltage at the bottom, as you change the resistance at the bottom, you change the voltage at the top. And this is the reason why. So, what you're going to do for this experiment is you're going to make a table, voltage and I. So by changing the resistor, you get different values here. And then you can get different values here. Now please note, you can get better equipment. You can actually get something like this. Resistor, ammeter, so you could get a machine like this whereby you can actually set the voltage at the start. So you can set this voltage and then you can measure this. So for example, you could put this at 1 volt and then you could measure. Then you could put at 2 volts and then you could measure. You could put at 3 volts and then you could measure. You could do it this way, but the problem is this machine here, it's expensive. So we're not doing it that way, okay? We're doing it this way, the old-fashioned way. It does the same job. As you change this, you change the voltage here, and you can see different values of voltage and of current. That's the key thing here. Do you understand? We are now getting a table of voltage and current. Okay, so let's continue then, which we've just done. So here's an example, and I need you to write this down. Well, actually, just before you write it down, so my variable resistor at the beginning, the resistance was 0, and then I increased the resistance, and as I increased the resistance, the voltage decreased. And what happened to the current? It decreased as well. Yeah? So what I would like you to do now, I want you to write this one down. Okay? Did you get it? Yeah? Okay, good. So, whoops, I shall draw it now. Here we go. Where's my program? Here it is. Alright, so the first column was voltage, and the unit was the volt, and the second column is the current, and the unit was the amp. Okay, what was the first voltage? It was 10, wasn't it? And then the next one was 9? Yeah. All the way down to 1. And then this one here was 20, and then it goes down 18 all the way down to 2. Alright, let's plot this. See what graph we get. This one, okay. Let's make straight lines. Next, next, next. Okay. IV graph. My first IV graph. On the x-axis goes voltage in volts, and on the y-axis goes current in amps. There we go. So not special, it's a straight line. So can you please draw this? They sometimes ask you in the exam to draw this, so just draw this as best you can. You don't have to make it accurate, try and make it accurate, but the key here is it's a straight line. No, don't worry about making it accurate, it's too accurate. Yeah?
It's like this, the direction.
What do you mean?
Direction.
It's upwards, yeah?
No, it's down.
No, it's upwards. No. This, look at this mathematically. What would I say the slope is here? Positive or negative? Yeah. The only reason it's decreasing is because voltage is decreasing because it's going backwards because of how you did the experiment. That's all. Oh, you've drawn this way too neat, too accurate. Okay. Most importantly, don't forget the names on the X and the Y. Yeah. Can I go on?
Yeah.
Yeah. So this is an important type of graph in electricity. So it actually gives us the definition of the lesson. The IV characteristics of a resistor is a plot of the current against the voltage when the power source provides a varying voltage. So in other words, the IV characteristics is this graph. You change the voltage, you get different current, and you put this on a graph. That's what I mean when I say IV characteristics. It is exactly, this graph is what I mean when I say IV characteristics. That's what I mean, okay? So please make note of that word in red, IV characteristics. Yes, got that? Yes? Okay. So now on to Ohm's law. So Ohm's law states for some materials at a low voltage and a low current and a constant temperature, the IV characteristic graph will be linear, passing through the origin. So look, what type of graph is this? Linear. And will it go through the origin? It will. So this is actually called Ohm's law, that the graph goes through the origin and it's a straight line. That's Ohm's law.
Write that down?
Yeah. what we know underneath this law is not always true.
What do you mean by it states here?
Ohm's law is, basically, yeah. This is not always true, though. So this doesn't seem great to have a law that's not always true. It's just true for a lot of the problems we look at. If it is true, then we say the material is ohmic, and otherwise we say it's not ohmic. So, just a little bit of English here. This word in red, ohmic, is an adjective. So, if this law is true, for example, if this law is true for this material, then we say this material is ohmic. So ohmic is an adjective, ohmic. Okay. So if it's true, we call it ohmic, and if it's not true, we just say it's not ohmic. Please note this adjective. Got that? So in the graph I drew, you see this graph here? I could say this material is ohmic because it's a straight line. So we can say it's ohmic. Alright.
You said the material which we used.
Say again?
The material.
Yeah, my made up sample here. If this was for some resistor X, then I could say X is ohmic. Whatever the resistor is. Yeah?
For the resistor, you say the material.
Yeah, the resistor is made of material, yeah. Okay, what I just need you to do is write down this table first.
You say example.
So this is an example question. Okay, got the table? Just the table. Right. Can I do this one now? Yeah. So the first question is draw the circuit. So the circuit looks like this. It's always like this. You have a power source. And then you have, I'll put the variable resistor up the top this time. Variable resistor. And then you have an ammeter. And then what you care about is you have a resistor here. And of course, yes, around it you have a voltmeter, and here is the ammeter. So what you do is you change this, which will cause this to change, and it will cause this to change. And that's how you make this table. Okay, so next let's make the curve. The circuit is the same circuit I showed you at the start, okay? Let's make the table. Alright, what was the first current value?
14.
14.
Yes.
Next.
13.5.
Yeah.
13. 12. 11, 10,
10,
8, 6.
8, 6,
4,
4, 2. Like this?
2. Yeah.
Okay, let's see what graph we get. Insert, chart, scatter, that one. Don't want this. IV plot. Example 1. Voltage in volts and current in amps. Now this one here is a bit different on purpose. It's not a straight line, is it?
Curve.
It's curved. So is it ohmic? No, it is not ohmic. Because it is not a straight line. So this is the curve you get. Okay, so what's the next part of the question? So look, when you don't need to draw this accurately, just in your notebook draw a curve shape. Okay. Voltage, current, and curve. Can I go to the next part? Let's see. Okay, so the next part here. Oh, I'm going to delete this table, okay? This graph. Or maybe I can just shrink it a bit. Yeah, there we go. The next question is, extend this table to include a row for resistance. So I want a resistance row here. So, resistance, what is it measured in? Ohms. And what's the formula for resistance? V over I. So the resistance here is V over I. So here's the value for resistance. Why did that one go to 0? Whoops, oh for goodness sake, go away. Yeah, right there. Oh no, it's not 0. Yeah, okay. What do you notice about the resistance? Yeah, when the resistance is, when the voltage and current is quite small, what do you notice about the resistance? It's constant, isn't it? 0.5 ohms. But when the voltage and current are large, what's happening to the resistance? Now look at the values.
Steady.
When voltage and current is big, how does the resistance compare? Is it bigger or smaller? Bigger. Bigger. So this material, as the voltage and the current gets bigger, you get more resistance. The resistance is not constant. For most materials, you get a straight line. And when you get a straight line, what do you have for the resistance? It's constant. Okay? So do you remember the example I did at the start where I got a perfect straight line? The resistance is constant for this line. Here the resistance is not constant. When the voltage and current is big, you have more resistance. But when it's small, you have constant resistance. Why do you think that is? Well, let me show you why. Oh yeah, and the last part of the question is, what's the smallest and largest resistance, and is it ohmic? Is it ohmic? No. And here's the smallest and here's the largest. Now, just to finish on this, here is V, here is I, here is my graph. The slope would equal this over this. This is the slope, which would be the change in the current over the change in the voltage. But you remember this formula, V equals I R. So I could have 1 over R equals I over V. So in other words, we get this result, that the slope is equal to I over R. Sorry, I over 1 over R, thank you. So big slope means small R.
If it's on it.
Hmm?
If it's on it,
No, this is always true. I know I drew it like a straight line, but it could be curved as well. And a small slope means big resistance. So this is important. Yep. Okay, so let's go back to my graph here. The slope, try and make this bigger. The slope here, is it bigger or smaller than the slope here? So this slope,
Smaller.
it's smaller than this one. So if the slope is smaller, then what do we say about the resistance? It's bigger. Small slope, big R. So as we increase, we get less slope. And if we get less slope, that means we get more resistance. And you can actually see that in my table I drew for you, which I can't get anymore. Well, you saw it earlier. The resistance got bigger. Okay? Right. So there are the 2 questions for you to do. You have to do the same thing, basically. Okay? And please note, in this first question here, I'm trying to trick you a little bit. You need to be careful because I'm using milliamps as the unit. See that?
So I have to convert it?
You can convert it if you like, yeah.